So this lesson here is integration by substitution. So what we want to do in this lesson today is try to recognize when substitution is required, make a change of variables, and then follow the steps to actually go through and do the antiderivative of a function. So what we're looking for here is sort of like comparable to the chain rule, and we're looking for the reverse of the chain rule to be happening. So what I'm really looking for is a function inside of a function. So you see that f of x is a function and g of x is an inner function for that f of x. If I notice that the derivative of that g of x sits on the outside of my integral expression, then it's like I'm just doing the derivative of the big part and ignoring this part because the chain rule is here. So you're sort of ignoring this part because the chain rule, when you end up multiplying by that derivative, will just go away. So for example, when I take the derivative of this side, I have how many functions? I have one function, it's f of something. So I do the derivative, which is f prime of something, times the derivative of the something, which is g prime of x. The derivative of a constant goes to 0, so I get exactly what I'm looking to do. So let's just go straight to an example. When we're trying to recognize this pattern, I take a look at the inner part of the function. In this case, it's sort of like an x squared plus 1. If I were to take the derivative of x squared plus 1, I would get 2x. And that 2x already sits on the outside of the function right here. So this is the proper pattern we need for chain rule. So we're going to do a change in variables. I'm going to let u equal x squared plus 1. Then the derivative of u with respect to x is 2x. Every part of my original integral needs to get replaced. So I'm going to treat the dx here as a differential, is what we call it. And I'm going to multiply both sides of this expression by dx. So I get du is equal to 2x dx. And now I'm going to do a change of variables. So in my original expression, whenever I see a 2x dx, that's going to get replaced by du. So I'm going to come back and write my integral expression. The stuff I boxed in becomes a du. The stuff that's underneath in yellow here, I've let u equal that expression. So this is going to become u squared. And now instead of having my expression involved with x's, I've replaced that expression in an equivalent way into u's. So now I just follow my power rule and do the antiderivative of u squared, which is u cubed over 3 plus my arbitrary constant, because again, this is an indefinite integral, so we need our plus c. Now, in order to complete our answer, our original question had x's in it, so I need to change my answer to have x's back in it. We know that I let u equal x squared plus 1, so now after I'm done integrating, I sub that u back in, so x squared plus 1 cubed over 3 plus c would be my final answer. Now, I'm always going to make you guys check your answer just for now, so that when you leave a test, you know if you're doing it correct or not. We're just going to take the derivative of the answer to see, have I done the process correctly? So I bring down the 3, leave the inside the same, and now because of chain rule, I multiply by the derivative of the inside, which is 2x. The 3 on the bottom is a constant multiple that just gets carried along. The derivative of c is 0. I clean this up, the 3's cancel out, and I get 2x x squared plus 1 squared, which is my original integral. So I know I've done this correct. Let's look at the next example. So I'm looking for something in the original problem that's sort of an inner function. When I look at this part here, this is sort of like a cos of something, and the something is the 5x. If I were to take the derivative of the 5x, I get a 5, and that 5 is already sitting on the outside. So it follows the chain rule sort of pattern. So we're going to let u equal 5x. Therefore, du dx would be the derivative with respect to x, which is 5. I multiply both sides by dx, which is 5dx. And now I need to figure out what my integral gets replaced with. So the stuff in yellow that I've highlighted matches up. So that becomes a du. And then my integral, the stuff in yellow should be the 5 and the dx gets replaced with a du, which is in yellow. The 5x gets replaced with u, and the cosine is just sort of an outer function that I can take an antiderivative of. So this is cosine u du. I take the antiderivative of cosine, which we know is a regular rule. So the antiderivative of cosine is sine of that u, and then we add our arbitrary constant. In order to find my answer, I need to replace the u's back with x's, and you can see that the u was in orange, and it was a 5x, so my answer is sine 5x plus c. So now I'm going to check my answer by just taking the derivative. You can either do this mentally or actually show it on the paper. I don't mind either way. I take the derivative of sine 5x, which is cosine of 5x. The derivative of the 5x is 5, so I can't forget chain rule, plus the derivative of the constant is 0. So I know I've done it correctly because this matches my original integral. Now there is an exploration here for you guys to look at. In this exploration, it just wants you to recognize, do you see that chain rule pattern happening? So if I look at the inner part of the function, x squared plus 1, the derivative is 2x. I notice it there. So yes, this follows the chain rule pattern. I look at the next example. My inner function is x cubed plus 1. The derivative of x cubed plus 1 is 3x squared plus 0. I notice that the derivative of that function sits on the outside. This matches the chain rule pattern. I look at the next example. The inner part of the function is tan x plus 3. The derivative of tan x plus 3 is sec squared x plus 0, so that works. Now what you're going to notice on these bottom examples is there's things that are missing, but the things that are missing are irrelevant. They don't affect your ability to do this type of integral by substitution. So the inner part of my function is x squared plus 1. The derivative is a 2x, so I'm missing a 2, but that's okay because I'm allowed to be missing a constant. Okay, we look at the next example. X cubed plus 1, the derivative of x cubed plus 1 is 3x squared plus 0. I have the x squared there, which is the important part. I'm only missing a 3. That's okay. I can make an adjustment when I do the substitution, which I'll show you on the next slide. Now, the next example, you'll see that, again, the derivative of tan x plus 3 is sec squared, but instead of something being missing this time, we have an extra 2 here, and that's okay as well because we can adjust for that. So as long as what you're missing or have extra is just a number, that's okay. If there's extra variables, that will cause a problem. So just watch for that. Extra variables will cause a problem. Missing variables will also cause a problem. These are both problematic situations. So let's look at some examples of how to actually do this when numbers are missing or extra numbers are there. So we look at our function. We say, here's the inner function, x squared plus 1. I take the derivative, I get 2x. I'm only missing a 2. So what I'm going to do is I'm going to put a 2 in there, but now I've changed the question. So I'm going to balance it out by dividing by a 2 so I don't change the question. So now my 2 is there with the x, and I sort of have an extra 2 floating on the bottom. So substitution will work. This method is called integration by substitution. We're going to let u equal the inner function, which is x squared plus 1. The derivative with respect to x is 2x. I multiply both sides by the differential dx. I get 2x dx. So now the 2x and the dx go together in orange.